Okay, today we're walking through 5 common programming concepts, specifically in the Rust programming language, creating variables and mutability. In Rust, when we create variables, we have to decide whether or not we're going to change them or not. Data types, such as scalar and compound data types. Functions, a grouping or a collection of statements that we can reuse. Comments, the primary commenting style. And lastly, control flow. There's a few different types: if, loop, while, for. These are some additional building blocks needed for you to build a functional Rust program. This chapter is covering stuff that you learn in every programming language. We're just going to learn how to do it in Rust. Variables, basic types, functions, comments, control flow. Keywords as well. They are in the appendix of the book. Variables and mutability is the first section. By default, variables are immutable, so once you store value in them, the intent is that they not change, and that you need to create a new variable in order to take a new value. However, we can still make our variables mutable. One of the things we're supposed to cover in this chapter is why Rust encourages us to use immutable variables. We're going to start a new cargo create, so cargo new variables. So it looks like we're going to do a little exercise where we create a mutable variable, we check it, and we try to change it and check it again. So based on what we learned about immutability, I'm guessing we won't be able to change the value, even though it lets us assign it. Or maybe it'll even throw a compilation error on the assignment. Let's see. Also, you'll notice in my videos in the first 2 chapters, I talked about not having IntelliSense working. When I restarted CLion, the JetBrains IDE that I have the Rust plugin installed in, then I got all of my auto-completion working. So you'll see that's here now. All right. And so we've got the confused crap. So that means it's not going to compile. We've got the IDE yelling at us. So if I hit cargo run without even scrolling down in the instructions, I'm guessing this is going to be unhappy. Yep. Can't assign twice. So by setting immutable variables, we can make assumptions in our code about whether or not that variable is going to change or not. I wonder if Rust has some common syntax when you name a variable that's immutable versus you name a variable that's immutable. Just a high-level question. Because if that's the case, then you might be able to just instantly, it's by convention, but you can instantly see as you're working on it, and then maybe at compile time catch you as a failsafe. I don't know. Let's see. So it says, hey, just change that variable to a mutable variable and move on. Cargo run is happy. So there's also constants. So you can make a constant and it is immutable always. You can never have a mutable constant. And this is for like configuration that lives in code, right? This is the usual all capital case variables with underscores that you see in most programming language to easily call out like, hey, this thing is a constant. One thing that's nice is the compiler can evaluate a limited set of operations. So notice this wasn't the exact value. It evaluated this math and then determined what the seconds were going to be. It's nice. There's also a reference of what you can evaluate for constant evaluation. We're not going to dig into all of this now, but it's good to know that's a thing. Rust also supports shadowing. I think the biggest key to learn here is that like when we're shadowing like this, we've effectively created a new variable. Next thing we're going to check out is data types. Sort of a reminder that you can annotate the type like this. What's cool is one thing I like that now that the IDE is working with Rust correctly, you'll notice that in my IDE, the types are inferred. So it's automatically determining that these are I32s. So if I wanted them to be unsigned, I'd have to type them myself, right? Like I'd have to colon U32 and take the variable, but by default, this is what it's doing with let. Scalar types, integers, booleans, floating points, characters. I just mentioned signed and unsigned. So you can pick your bit length. What's interesting is you can declare architecture. So you can match the size of the architecture you're on. So if you're doing some embedded Rust and you happen to be on some, I don't know, 16-bit system or 32-bit system, you can make your code more compatible, I guess, as long as it's able to figure out what the architecture size is of the thing you're compiling on, which it would know at compile time. It can make sure that the variables fit. You probably have to think about like code bounds. In other words, like if you do architecture and you are compiling on different architectures, at which point you'll overflow your integer is different. So you'll have to think about that. Signed numbers are stored using 2's complement. It's been a while since I've seen that. You have multiple ways you can represent integers. Integer defaults to I32, which is what we saw in the IDE. Of course, they mention integer overflow here. I just mentioned it as well, so let's see what they have to say about it. Yes, so interesting, on debug mode, it'll panic if your integers overflow, and prod doesn't want to crash your program, so it'll overflow, but we consider overflow errors. Don't use overflow as a side effect is what they're saying. And I was just mentioned about you have to handle the overflow, so they have some methods that you can use for that. So you have the wrapping add, overflowing, saturating. So a character in Rust is always 4 bytes. Got it. And so the intent is that it can cover Unicode characters and more. They go out of their way to mention a character isn't really a concept in Unicode. So your intuition of what a character is may not match up with what a char is in Rust. I get what they're saying, right? I just mentioned how in Unicode characters are actually variable length, or symbols is a better way of referencing it. Like symbols are variable length, so they could have variable byte length, 1 byte, 2 byte, 3 byte. Go deals with this by making a concept of a rune so that it only always holds a character at its minimal byte length, but then that means runes are variable sizes. And I think runes are only 1 to 3 bytes, so they're saying, oh, in Rust, everything is 4 bytes when you declare char. So you can have a bunch of padded space depending on what's being used in your memory. I mean, I doubt it's that inefficient, but just a matter of knowing that you're not always going to fill the 4 bytes. Although, how Rust actually deals with these 4 characters, it looks like storing UTF-8 encoded text in strings in Chapter 8 is going to be a good place to explore that more. All right, so we're covering functions now. Quick first thing you need to know, functions are declared using this FN signature. Main is a special one. Every program requires a main, and then your other functions can be anywhere. They can be before main, they can be after main, they can be in different files, but you have to have a main, and then you can call other functions from that environment. All functions should use snake case when you're writing them. So that's what the style convention is for Rust, is to use snake case and when you're doing declaring your functions. And then also parameters. So when you define that function template at the top and it says, hey, this is the parameters I take in, you have to make sure that you declare the types up front. There's a nuance here with Rust that's worth discussing with this concept between statements and expressions. Statements are a set of instructions that perform some action but don't return anything, and expressions evaluate to a resulting value. So we're going to play with some statements and expressions here. The book wants us to try out this syntax. Let x equal paren, let y equal 6. We already see that the IDE is yelling at us, so it's probably not going to be happy. Let's see what happens. Right? Varied declaration using let is a statement. So remember, statements don't return values. Expressions do. So you can't have a variable with a statement on the right-hand side. So then the question is, well, is this any different? Short answer is, I don't think so. Right? If you look at this, what you see is we're attempting to declare a variable, and without the parentheses, this even looks weird. So let's see. And it's yelling at the parentheses. Expected expression, remember expression returns value, but instead you got a let. And we know that's going to fail. Still, statement. All right. can we declare two variables at a time? Right? Let x equal y equals 6, right? That would allow us to say, hey, create the variable 6 and x. I'm sorry, create the variable x and y and make them both equal to 6. Is that a thing? Oh no, we don't know what y is. Some languages do that, like with a comma. And in this case, it doesn't look like it. It's already saying, hey, you don't have to, like, you've got this word comma. So it doesn't like any of those things. And that's basically what this section of the book is talking about. So what can you do? So we've got y that's going to equal this statement and an expression. So let x equal 3, and then we just have a, bam, 4. So why does this work? So let's take a look at this function. Doesn't say return anything. So the value of y is 4 still, but now the value of x is 5. So we have a function. I don't see the word return used anywhere. I just see a statement. It looks a lot like this line, right? What's going on here? You can return early from a function by using the return keyword and specifying a value, but most functions return the last expression implicitly. So this is an implicit return and this is an implicit return, which means these are now expressions because expressions return things. One interesting note is we don't have a semicolon here, and if you notice a lot of our other lines we tend to add those. So what happens if we put a semicolon here? Whoa, one little semicolon and this blows up. What happened? And I think the answer, based on what we're learning, is that when you drop that semicolon here, it becomes a statement and is no longer implicitly returned. So this entire bracket here no longer becomes an expression that can be stored in the variable of y, which fails. So there's that little nuance around expressions and statements, and you can have an expression that turns into a statement. So this is going to be something to pay attention to. So comments are super straightforward. They want you to use this / notation. They want to let you know you can also comment at the end. So that's the preferred method of commenting. They also mentioned that Rust also has another kind of comment, documentation comments. So we'll get into sort of what the doc comments look like in chapter 14. So in this section, we're going to cover control flow. As I mentioned beginning of the video, there's 4 main types of control flow: if, loop, for, and while. So we're going to cover those 4, a couple of examples, and go from there. So we're looking at an if example. So what we're doing with if is just doing a direct condition comparison. And after that condition comparison, it determines which block you go into. We also support else. Also, what happens if you get rid of the actual operator here? Hey, like that's not a Boolean, right? So that's what we expect. Also, just like other languages, else if is also possible here. If we think about what we talked about earlier around statements versus expressions and how not having a semicolon generates an expression and how expression returns values, and if expressions return values, then what they're talking about here is interesting. This is going to be true, so we're going to print 5, right? Because it's an expression within the 2 curly brackets, actually 2 separate expressions. And if this had a semicolon, it would turn it into a statement. And look at that, failure. We can run it to get official compile failure, but we know it's not going to succeed. And it's even smart enough that it has this little blue line here saying, consider removing this semicolon. I don't know if I saw that in the last chapter where it talked about expressions and statements, but that's pretty cool. It's trying to help you debug this problem. It's like, hey, either something's wrong with this 6, but most likely something's off with this semicolon. Also, it's saying, hey, what happens if you mess around with types? So first thing I noticed here is IDE is not saying anything about this. like the IDE caught the last problem, but we believe that's going to be an issue, and it is, which makes sense. Also, just interesting how the last scenario with the statements versus expressions, the IDE picked up on that, but it didn't pick up on this extra condition. But the compiler did, and it called it out pretty clearly. So outside of if, we then go into loop, while, and for. Loop is straightforward. You have a bracket, and you say, hey, whatever's in here, you can actually run this collection of statements. If you're using loop, you're going to need to actually break out of that loop. So whenever you hit your condition, break. This is interesting syntax here. So let's explore that one. So the result was 20. So once the counter got to 10, it braked. Right here, returning counter times 2, which then went into result. And so break must be acting like a return value here. We have a semicolon, so it is a statement, but break must somehow be returning this statement. Let's see what it says. We use the break keyword with the value. We use a semicolon at the end of the statement that assigns the value to the result. One of the uses of loop is to retry an operation you know might fail, pass that result out of the loop into your code. To do this, you can add the value you want returned after the break expression and use that to stop the loop. So it's like a return from a function, but also killing the loop at the same time with the word break. So that's interesting. Instead of just looping and having to call out break, you can put your end condition right here for while. Pretty straightforward, common stuff. The thing that I like about for loops is that they already work with iterators. So if you have a array like this, you could say for element in, you just iterate over it. You can do it over slices. This is an interesting little reverse command they're calling here. So at the end of the day, we just went over those main conditions, and what we get into at the end of chapter 3.5 is saying, hey, try an exercise. Why don't you try to use what you've learned up to this point to build one of these sample applications? So the samples they give here is a temperature conversion between Fahrenheit and Celsius, generate the nth Fibonacci number, and print the lyrics of the Christmas Carol, the 12 Days of Christmas. I've chosen to do convert temperatures. So let's check that out. All right, let's walk through this quick and dirty temperature conversion program. So we're converting from Celsius to Fahrenheit and Fahrenheit to Celsius. I went ahead and made some options to do both. So let's see what I finished up with. We're creating a mutable response string, a mutable input temperature, and a Boolean flag to just determine whether or not we're converting from Celsius to Fahrenheit or Fahrenheit to Celsius. So ask the question, what do you want to do? Yes or no? Again, this is similar to what we were doing when we did the guessing game. So a lot of these constructs are what I learned when I did the guessing game. So I didn't add anything particularly complicated. I didn't go to future chapters. I just used what I learned in the guessing game. Guessing game is chapter 2 if you were following along. So captured that value, stored it in response, trimmed it, made sure it was all lowercase, and then I do a check. How you responded to this question. If you responded with some form of yes, then we're converting from Fahrenheit to Celsius. I make this super simple. Like, I don't do that much checking here. So you can basically put in anything that's not yes, and it will do Celsius to Fahrenheit. Input the temperature, capture that in input temp. Then we need to convert that into a float. So if it throws an error, it says, hey, please enter a number. And then from there, based on that determination of whether or not we were going to Celsius or not, we do this quick check. And depending on what's happening there is which function we run, F to C or C to F. Both of them are defined here. And I just dropped the little formulas for C to F and F to C in here. So what happens when we run it? I did a little refactor right before recording this. So I left an old variable name in there. So align those variables now. Should be happy. Also, it looks like it's complaining because I import something that I don't use. Let's get rid of that. See if we can get rid of these warnings. Bam. What do you want to do? Right. So we're going to do Fahrenheit to Celsius. And I think we can do something like, I don't know, what's 75 degrees? 23.888. All right, let's run it again. So this time we want to go the other way around. So I think 32C should give me something nice. I think it's the other way around. If I do 32F, get 0C. Let's do that one more time. So I got 89.6 degrees. And let's do no. And 32. Yeah, there we go. 32, 0. Bam. So that's the end of the guessing game. Not guessing game. This is the temperature conversion. So that's the end of the temperature conversion. Quick knowledge check. Did I actually learn something? Could I write a program? Yes. Like my third Rust program, making progress. As you can imagine, there's almost 20 chapters in this book, and this is the end of chapter 3, so we should really be building up a good body of knowledge. Thanks for sticking with me to the end. Please subscribe to catch new content, and also there's a playlist of all of the Rust videos that I'm making around this Rust book and some extra stuff that I'm making. So check out the playlist if you want to see some other videos related to this. Until then, Curious Tech out.